All right, welcome back. Hey, after that last one that exhausted me and I had to call it a night last night, this one's surprisingly straightforward and easy, especially if you've already watched the video that we put together for the Google Meet last time. For those of you that were for that sort of lecture of the introduction about Doppler effect. We talked about double Doppler on that one, and so this is pretty straightforward relative to the other one. So let's see what we got going here. Looks like we have a car radar from a police car that comes out and is reflected, and we think of that initial impact happening there with the car moving as one Doppler effect occurring, and then the reflection itself coming off as being the second Doppler. So this red car acts as a receiver and then as a transmitter, and so we get both Doppler effects happening, and that's why we call it double Doppler. Looks like the police car's using 19 gigahertz microwaves. And the first question asks, what's the wavelength? Well, you got to remember that microwaves are a form of electromagnetic radiation. I refer to all of that as light. I don't worry about whether it's visible light or other types of light. They're not visible. I just call it all light. So microwave is light, which is to say it's electromagnetic radiation, which means it's going 3 times 10 to the 8th meters per second. So that's a pretty straightforward calculation to figure out the wavelength when we know the speed and we know the frequency. That's an old topic 4 question, actually. Which equation should we use for Doppler and why? Because it's electromagnetic radiation, we're going to use this form of the Doppler, right? Because it's light. We'll be using this one, and specifically we'll be using the frequency part of that. Let's see what I do here. Oh, up here is just showing the work of 19 gigahertz turned into just hertz because giga is 10 to the 9th. Then use V equals frequency times wavelength to solve for wavelength. So wavelength equals velocity divided by frequency, plug and chug. And you get this number in meters, which is about 16 millimeters. The red car acts as a moving observer and then also as a moving source during the reflection. Thus the Doppler effect happens twice, is what I'd like you to say there. Very straightforward. Now they want to see what that change in frequency is. Now the frequency is really big, times 10 to the 10th. The change in frequency will be very small, and the change in frequency is what they're asking for here. So this delta F is what they want. But when we're going to plug in V and C here, we need to have the same unit. And C is in meters per second, so we need V to be in meters per second. So a little unit analysis here, where we have kilometers per hour, and hour in green. I'm canceling the hour here, so that helps me know that I need to divide by the 3,600. And kilometer here is going to cancel. These are conversion factors, right? Just do a little unit analysis here, and we can get that it's 69.44 meters per second if it's 250 kilometers an hour. Anyway, that's what's got to go plugging and chugging into this thing. So we put the 2 because it's double Doppler. We put V in meters per second. We put it C, which is speed of light, times the frequency that's being altered, the initial frequency here before it got altered, and we get the change in frequency, which to do sig figs is about 88,000. Now that 88,000 change in frequency is observable by the police car. The little instrumentation there that receives it looks for the change in frequency between what it knows it's sending out and what it's receiving, and then compares them, and the difference between them indicates sort of doing this whole problem backwards, how fast the car is going. So that's double Doppler, nice DDD that gives us a little bit of a break because this one's pretty straightforward, and I hope that helped you out a little bit, and see you soon.